So you can hear, I need you to talk. I also want to see if I can hear you too. I need you to
Hello,
talk.
can you hear me?
You, you said that again?
Can
Can you?
you hear me?
Yeah, I can hear you. Thank you so much. Okay, so I also need something online to confirm if you are seeing the lecture note that I'm projecting now. Can you see the lecture note, the person online?
Yes.
Thank you so much for confirming that. Good morning, everyone. I want to welcome you to another beautiful week. Of course, today we're actually going to walk through another exciting statistical topic. But before I get started, I got some announcement to make, even though I've already sent a message through announcement section, but I need to repeat this, because I know some students might have missed that. The midterm one exam will be reading between June 23 and June 24. So which means you're actually going to have access to the exam on by 6 p.m. on June 23rd, which is on Friday. And the exam is going to be left open for more than 24 hours. Except that if you click on start, you're only going to spend 90 minutes. Does that make sense? But you can decide to start at any time within the time the exam will be left open. So I needed to be flexible because I know you got a lot of activity going on in the summer. There's going to be 22, there's going to be about 20 to 22 multiple choice questions, and there will be two short answer questions that will be targeted towards R. Of course, you saw the way I gave you assignment one. The way, if you look at problem 3 in assignment 1, of course, I wanted you to make use of R. So the solution to assignment 1 has already been uploaded on Canvas. You can check. And of course, my TA, I know she has started the process of grading that. And you know what you basically going to be formed, well, that will form midterm 1 is what we did in week 1, week 2, and what we're going to do today. There's possibility what we want to do today may be part of the midterm 1. Okay, so let's get started. So once again, I want to introduce you to this topic, inference on regression coefficients. In the outline, I'm going to talk about inferences about the slope, inferences about the intercept, and correlation and test on its significance. Just like the way I always do, how do we find ourselves, you know, working on this? I want to have a kind of recap on how we find ourselves, you know, discussing this particular topic. The whole idea started from characterizing relationship between two variables, one dependent and one independent. We basically want to figure out what is going to be an appropriate relationship, and we are assuming a straight line. Okay, we're assuming a straight line. Of course, I've walked you through how to estimate parameters in linear regression, both the slope and the intercept. And I've also walked you through how to investigate whether assumptions hold. Assumptions of linearity, normality, constant variance, independence, and something I'm going to call absence of unusual observations like outlier or high leverage and the like. And if there's a problem, of course, I've also walked you through how to fix that using the idea of power transformation that we did the other time. What is next? I think I've also walked you through how to make a prediction. I remember I walked you through individual prediction, I call prediction interval. I also walk you through the confidence interval of prediction that I actually call the average one. Now, what is left undone? What is left undone is now, can we have a way to make a judgment about our model? If you take a look at the title, right? If you take a look at the title is called inference. Inference means judgment. Judgment. Okay? That's what inference means. It actually means judgment. Okay? So how can we begin to trust our model the more? Okay? By way of inference. When I say inference, inference on what? Oh, that was why I said inference on the slope. Because on the inference on the slope, there are two things we're going to do. We're going to test hypothesis about it. Because why are we testing a hypothesis about slope? We basically want to know whether the slope value we got is statistically significant. We also want to see whether the intercept that we got is statistically significant. So because of that, we're actually going to conduct an hypothesis testing on slope. We're also going to conduct a hypothesis testing on intercept. Not only that, we're also going to construct a confidence interval on slope and confidence interval on intercept. You know what we've done before is talking about the confidence interval for prediction. That is a different one. This one is like confidence interval for slope, confidence interval for intercept, and I'm actually going to tell you the implication of what we're doing. Then lastly, what is the relationship between regression and correlation? How can we actually test correlation value for significance? I'm also going to walk you through that today. All what I just need from you is basically to pay attention to all what we're going to be doing. Now take a look at this. I want to conduct an inference on slope. Conducting an inference on slope means I basically want to figure out how significant is the value of that slope before we can trust our model. We need to first investigate how significant is the component in the model. One of the components in the model is the slope. And let me tell you this, don't forget, we basically want to characterize relationship between y and x, right? Now, when we are conducting hypothesis on slope, we're actually going to state what I call the non and the alternative hypothesis. You know what that guy is talking about? HO, beta 1 equal to 0. Beta 1 equal to 0 means there is no significant linear relationship. Beta 1 equal to 0 can be interpreted to say slope is not significantly different from 0. It is not until it's exactly 0, we could have some values that is not exactly 0, but they are not significantly different from 0. There's a difference between when you equate a value to 0 and when you say it is not significantly different from 0. You know what? Some of you may be wondering, but you've already used a residual plot. Residual plot has already told you that there's a linear relationship. What are you worrying about again? The residual plot cannot tell us whether the linear relationship that exists is significant. I'm going to say that again. The residual plot can only tell us, oh, linear relationship exists or not, but it cannot tell us how significant it is. If I want to know how significant is a linear relationship, I need to conduct this test. Does that make sense to everyone now? And when you are conducting a statistical test, you need to specify what is your HO. Your HO is the non-hypothesis. Okay, non-hypothesis. Non-hypothesis HO. The non-hypothesis is an hypothesis of no effect. No effect. That was why you say beta 1 equal to 0. You know what? If beta 1 equal to 0, it means there is no connection between y and s. Imagine you have a model y equal beta naught plus beta 1s, and this guy is already 0. If this guy is already 0, you know what you're trying to say? You're trying to say y does not depend on anything. That's what it means. You're only going to have the values of the intercept. Why, if you take a look at the alternative, the beta 1 not equal to 0. Beta 1 not equal to 0 actually implies that a significant linear relationship exists. Does that make sense? If you want to conduct a statistical test, you're actually going to begin by specifying your non and the alternative hypothesis, just like what we do in the court of law when the court want to entertain a case. The very first thing they're going to say, okay, are you guilty or not? There are two hypotheses before the court of law. We're also going to have two hypotheses before us. Now, the next thing now is, if I want to test this hypothesis, I need a test statistic to be able to do that. What is a test statistic? That is what I'm displaying now. B1 minus beta 1 divided by that SB1 is the one that I call the standard error of the slope. That lowercase b1 is the value that you obtain for the slope. The beta 1 is 0 under hypothesis. And of course, in a mathematical form, the standard error is that guy. You know, when you see x, y, you know, when you see that I wrote, okay, even though arrow is going to do all of that for you, you're basically going to see, okay, so the xb1 that are always, that you can also call the standard error of beta 1, okay, you know, I said is this guy divided by this guy, okay, so what that means is that this guy here, okay, is basically going to be the sigma, okay, the residual that you're actually going to see, and I'm actually going to show you all of that. So, which is the same thing as the sigma cap that I'm actually going to call residual standard error, okay? But let me show you an example of how it's going to be. Let's go into an example now. Produce store. In this example, we're actually considering 7 stores. Don't forget, we already take sample, right? Okay. Now, in these 7 stores, we have information about the square feet. And annual sale. You know, at times, some stores may basically want to expand. Why are they expanding? Maybe they are expanding because they realize that maybe the more square feet, the more sales. Okay. Now we want to investigate that. Is that true? We basically want to know relationship between square feet and their annual sales in thousands of dollars. So we want to basically look at the relationship that exists between the square feet of a store, okay, the square feet of a store and the annual sales in terms of, you know, thousands. We got 7 stores, and the data set available on 7 stores. We feeded the model. Of course, you know by now how to feed. a linear regression model, and we got our beta naught to be 1636.415, and we got our beta 1 to be 1.487. Okay, and of course the slope of that is 1.487. But the question now is, are square footage and annual sales linearly related? Of course, you can answer, when you take a look at the residual plot. Okay, of course, maybe we've already investigated where absorption hold, and if everything looks so good, like I said, residual plot cannot answer how significant is a linear relationship. Now, if I want to do this in R, like some of you that may be wondering, what am I going to put into R? I'm going to demonstrate that to you now. Take a look at that. That's an R code. Square feet, I put the values under the square feet. I put the values under sales. If you copy all of this into R, if you just copy and paste this into R, this is what you're going to see. You're basically going to see results. This is the output. Okay? Now, I want us to make sense of this output. This output actually has a lot of information. Let's start with the very first thing that you're seeing, residuals, right? Do you see residuals? The value that you're seeing, negative 521.3 to 171.6, are the residual values for each store, which is a difference between the original values of the dependent variable minus the predicted. Do you remember that? That was what was automatically computed for you. Does that make sense about the residuals now? Now, another thing you're going to pay attention to, let's look at the first column. Let's look at the estimates. Under the estimate, you can see the very first value that falls on the intercept 1636.415. That is our beta naught cap. Then 1.487 is actually the slope value, the beta one. I mentioned something the other time about standard error, right? The standard error of the coefficient. Take a look at that. Under the standard error, the standard error of the intercept is 451.495. The standard error of the slope is 0.165. Take a look at that. If I want to conduct inference on regression coefficient, okay, I need their corresponding standard error and their estimate. I'm going to say this again. Anywhere in the world, if I basically want to conduct inference on regression coefficient, okay, conducting inference means it's either I want to test hypothesis about it, or I want to construct a confidence interval. Inference is about two things: testing hypothesis, constructing confidence interval. Now I'm going to repeat myself now. Anywhere in the world, if I basically want to conduct inference, that is, I want to test hypothesis, or I want to construct a confidence interval, I need the standard error of that store. Okay, right now, you can see for 451.495 is the standard error of the intercept. If I want to construct hypothesis about intercept, or I want to construct a confidence interval about intercept, I need that guy, standard error. Does that make sense now? Okay, now the test statistic value. You remember the other time I said the test statistic value is the estimate divided by the standard error. If you take a look at the table, you can see a t value, right? That t value is actually, what is this? I'm actually gonna write now. Okay, so that t value is this guy. So it's actually this guy minus this divided by this. So in this case now, you know what I'm trying to say? If I'm testing hypothesis about the slope, okay, if I'm testing hypothesis about the slope, this is going to be my test statistic. My if about the slope, I'm actually going to write 1.487 minus 0 divided by what is the standard error for slope? 0.165. Okay, and in the end, that will give you 9.010. Do you see that? You see that? You can see that everything is already done for you when you run a code. Okay, now if I now want to take a decision on whether I should go with the non-hypothesis or I should go with the alternative hypothesis, then I'm basically going to look at the p-value. Okay, I'm going to look at it. Look at, can you see the last column, right? Okay, that they wrote the probability or greater than the absolute value of t, right? You can see that, right? That is what we call p-value. That's what we call p-value. Okay, p-value is the probability of observing extreme value when the null hypothesis is true. Now, what we do in statistical analysis, if we want to take a decision, like I said, if you take a look at this is step one. Okay, specifying the hypothesis. Step two, your test statistic, and you have a result. Okay, step three, your p-value, right? Like the p-value for the slope there is 0.000281, right? And if you write is 0.000281, then your step four now, okay, your step four now is decision rule. Okay, what is the decision rule? Decision rule states that the non-hypothesis should be rejected when P, now this is reject HO if P value is less than alpha. Okay. Oh, this of you online, can you see what I wrote on the board? This of you online, can somebody confirm that by talking?
Yeah, I can see it.
Thank you so much for confirming that. Okay. The alpha is a level of significance. Okay. You'll be given that. Alpha means level of significance. Okay. Which at time we take at 5%. Okay. Now we reject H naught if the p-value of your test is less than the given level of significance. Otherwise, okay, we fail to reject H naught. Now, for the case of the slope, the p-value that you have here is 0.000, which is less than 0.05. And what are you going to do? You are rejecting this guy. Rejecting the non-hypothesis, you know what that means? It means you're actually going to conclude in favor of the alternative. You know what that means? This guy is trying to tell us the slope here is significantly different from zero, and that confirms the linear relationship that exists between y and s. Our y and s here is the square feet, and the annual sales is statistically significant. That's exactly what we mean. Okay, and that was why we're taking this decision now. Do you see that? We reject a show. Okay, the evidence. Okay, there is evidence that the square footage is linearly related to the annual sales. Before we can make that conclusion, then we need, even though we have investigated assumption violation, no any assumption is violated, we still need to do this. Does that make sense? Until we conduct a statistical test. And that's exactly what we've done. Okay? Is there any question on this? Now, I told you something the other time. I said when we're making inference, we can make inference in two ways. One, by hypothesis testing. The second one, by confidence interval. But let me tell you this. I'm going to tell you how we can also use confidence interval to do the job of hypothesis testing. That's what I want to do now. Now, take a look at it. This is now. If I want to get the confidence interval of the regression parameters in R, you're going to write confit into module. Don't forget, go and take a look at this. Module, in the code. Do you see this guy? Module, model equal lm. Do you see that, right? Okay, so if I ask you, in fact, I think in the ongoing assignment, I think I asked that question. Okay, if you want to get a confidence interval, okay, the confidence interval for regression parameter is just going to be confit into that. Do you know what I'm having now? It will automatically give you the confidence interval for intercept and for slope. Now, you know what I want us to do now? I want us to listen. I want everyone to listen. I want to make an interpretation of this slope, of the confidence interval for slope. Why do we need confidence interval in the first place? I think I just told you why we need hypothesis testing, right? Why we need to test. We conducted hypothesis testing the other time on the slope because we basically want to see whether statistical, whether significant linear relationship exists between the two variables under investigation. Now, why do we need a confidence interval? Of course, there's more than one reason we need a confidence interval. Okay? A single value, a point estimate could be wrong. Okay? Then we needed to incorporate a margin of error that will actually put into consideration error to the left and the error to the right. With a confidence interval, that will give us a way to describe our result in an interval in such a way that all of them cannot be wrong at the same time. But do you know another reason why we conduct a confidence interval? It will tell us how reliable is our estimate. Which estimate? For instance, take a look at the estimate. For the intercept, how reliable is 1636.415? 1636.415 is a point estimate, a single value. It could be wrong or right, even if you have done the necessary things. The one for the slope, 1.487, is also a single value. It's a point estimate. It could be wrong or right, even if you have done what you are supposed to do. And therefore, the idea of, constructing a confidence interval will enable us to tell how reliable is the estimate. Okay, now I want to take a look at the confidence interval now. For the square feet, if the confidence interval go from negative to positive, I'm going to say that again. If the confidence interval go from negative to positive, of course, negative to positive included zero, right? It means there is zero in the interval. When you have zero in the interval, that will favor the non-hypothesis. What is that? Zero in the interval. If a confidence interval should go from negative to negative or positive to positive, that is supporting alternative. Is there an agreement now? Look at that. That is positive to positive, which means the decision we took conducting hypothesis test, there's an agreement between them. The other time, the non-hypothesis was rejected, right? Because the p-value of the test was less than the level of significance, which means we rejected this guy. We conclude in favor of this. What I'm telling you now, okay, agreement occur between confidence interval and hypothesis testing if you take a look at that of the square feet now, you see that it is from positive to positive. There is no zero in the interval. No zero in the interval means we are rejecting this guy. This is what we are accepting. Does that make sense now? So what if we ask you to use the confidence interval to take a decision regarding the significance of the slope? Or you want to take a decision regarding the significance of the intercept? Take a look at the intercept as well. 475.80903 to 279. That does not include 0. You know what this is telling us now is that our intercepts and our slope are significant. That's what I mean. They are significant. They are significantly, when I say they are significant, you know what I mean? They are significantly different from 0. That's what I mean. Any question? Any question? If you go back, take a look at this guy. If you want to look at the how significant is the intercept, do you see the p-value of the intercept is 0.0154 0.015149? That is also less than 0.05. Okay, as you can see in the summary, the p-value of both the intercept and the slope is less than 0.05, which is indicating the intercept is significant, the slope is significant. If you take a look at the confidence interval too, there is an agreement because none of the interval includes 0. When the interval includes 0, that shows insignificant. Insignificant. Insignificant means the null hypothesis is true. Significant means alternative is true. Does that make sense? Okay. Now, this is a conclusion. At 95% level of confidence, the confidence interval for the slope is that, and that does not include 0, like I said. If it doesn't include 0, that actually means significant. Then I'm going to have a conclusion now. Look at my conclusion. There is a significant linear relationship between the annual sales and the size of the store. Initially, maybe the residual plots already said that, oh, linear, this is linear, but residual plot cannot tell us how significant is a linear relationship. Does that make sense now? If you really want to tell how significant is linear relationship, it's either you conduct hypothesis testing using the t-test, or you actually construct a confidence interval. Now we got another test that we call f-test. What do we do with the f-test? The f-test is basically going to test significance of the overall parameters in a model. But you know what? There's no difference between f-test and t-test for simple linear regression. I'm going to say that again. Whether t-test or f-test, there's no difference between them when it comes to simple linear regression. What do I mean by simple linear regression? I have one dependent and one independent. That is what make it to be simple. Like what we're going to be starting tomorrow is multiple linear regression, where we're going to have more than one independent variable. In that situation, the f-test and the t-test will not be the same. But when it comes to simple linear regression, the f-test and the t-test is basically going to be the same because they're all going to be focusing on one slope. Okay? We're actually going to talk about one slope because we have one independent variable. The only factor we're considering here is a square feet, right? As it relates to annual sales. Okay, so, but I want to look at the SSR. You remember? That is sum of square regression. You remember we've done it in the class when I was talking about partitioning of the sources of variation around the response. You remember, okay, divided by 1, the SSE is the sum of square error. You remember the sum of square error is unexplained variation, while the SSR is explained variation. What is the meaning of that one? SSR divided by 1. 1, that is the degree of freedom. Like how many parameters do I have in a simple linear regression? How many parameters? 2. Beta naught, beta 1. What is the degree of freedom? 2 minus 1, 1. That's why you see SSR divided by 1. Then what is n minus 2? Of course, that is the degree of freedom for error. The degree of freedom for error is n minus 2. I think you take note of that. Okay, now there is a mathematical relationship between T and F. Okay, T and F, the mathematical relationship is when I square T, that will give me F. Take a look at that. When I square T, that is basically going to give me F. Now the question now, what is the appropriate code? Like if I want to run this in R, how will I get F test? Like if I want to conduct F test in R, F test is also called ANOVA test. You're just going to do ANOVA into module. Look at that, ANOVA into module. You remember your module, right? ANOVA into module. This is going to give you this. This output here is different from linear regression outputs. This output here is this is giving you the partitioning of the variation around the dependent variable to explain and unexplained. 30380456 is sum of square feet. That is the explained variation. 1871200 is the unexplained variation. Does that make sense? So the essence of this code is just for you to be able to see how the variation around the dependent variable can actually be partitioned or broken down into explained variation and unexplained variation, as you can see. Now, what is the essence of the p-value here? If you look at before the p-value, do you see the f value? 81.179 f value is like we've made use of this particular formula. Okay, I needed to pay attention to this now. What if I actually ask you to compute that? Even though R has automatically computed that for you, but I needed to see this guy now. I needed to see this guy now. Okay, those of you online, can you still see my board, and can you also see what I'm projecting? Lecture slide, can you see that?
Yes.
Thank you so much. Now, F is XXR divided by 1 divided by XXE divided by N minus 2. You know what I'm trying to talk about? Okay, now this has already been computed for you, okay, by R, and this is trying to tell me my result is 81.179. You know what that means. What is the SSR from the table? The SSR is the sum of square feet, which is 30, which is 303380456. Okay, divided by 1, then divided by what is SSE, the sum of square regression, 187 1200 divided by, okay, if I want to know the N minus 2, okay, I can go back to the linear regression one. If you take a look at this, okay, the N minus 2, of course, how many stars do we consider? 7 stars, right? 7 minus 2, that will be 5, right? Okay, that is why, see, the degree of freedom for residual, what is it in the table? 5. Can you see that? So when you compute this guy, it will automatically give you this guy. That is the F statistic value. We call this guy now, okay, F statistic value. What if I ask you to show all of that? Okay, now what is the p-value now? You're now going to look at the p-value associated with that. I wanted to look at the p-value here for the F and the p-value that we got for the slope. Can you see the p-value that we got for the slope? Is 0.000281. And let's look at the p-value that we got for the f-test. Also is 0.002. What did I say the other time? I said for simple linear regression, okay, the p-value for the t-test will be the same as a p-value for the f-test. But you know what? The difference is going to be in terms of the t-value and the f-value. Take a look at this. I said they have a relationship. When you want to look at the t-value, I'm not talking about p-value now. They're going to have the same p-value, but there's going to be the difference between t-value and f-value. What is the relationship? When I square t-value, that will give me f. Now let's go to t-value. What was the t-value? What was the t-value for the slope? 9.010, right? Can we square that? When you square 9.0, let us now see whether that will be equal to the f value. I think when you square 9 point something, that will be 81, right? Okay, you're going to see for f value now. Oh my God, look at the f value, 81.179. Can you see that? When you square t value, it will give you f value, okay, which means they are not the same, but they will have the same p value. Does that make sense now for simple linear regression? Okay, any question? I'm done on simple linear regression. I want to go into correlation. Some of you may be wondering, what is the difference between regression and correlation? Correlation measures, the strength and the direction of the relationship between variables. When I say strength, okay, is it weak? Is it strong? Is it perfect? That's what I mean by strength. Strength, okay? I mean this guy here. The strength and direction, okay? But the correlation will only tell us the relationship. We cannot use correlation to make prediction, but regression can be used to make prediction. Can you see the difference between them? Okay, the correlation will tell us, oh, relationship that exists is positive or negative or weak or strong or perfect. But correlation cannot tell us how we can make a prediction of Y based on X. But regression does. Now let's look at correlation now. I just told you about what it does. Okay. Now the formula for correlation, of course, you've seen this before. Probably in your high school, right? Based on X and Y, right? And you remember when you are constructing a scatter plot. This is exactly, you're doing correlation, which means in regression analysis, you are also doing correlation because of the fact that you actually going to start your part of your preliminary investigation is to construct a scatter plot, right? When you are constructing a scatter plot, that's a correlation. Now, your scatter plot, the first one here is when R equal to -1. That's a perfect negative correlation. Okay, so take a look at every other one from perfect negative to perfect positive. But let me tell you this, in a stochastic world, we can never have a perfect correlation, whether negative or positive. And that was why we don't normally have all points. All points cannot fall on a straight line. It's not possible. If all points fall on a straight line, we will never call it a scatter plot. Why do we call it a scatter plot? We call it a scatter plot because some points scatter away. Does that make sense now? Okay. Now, we use rho. Okay, that very rho is population correlation, while R is a sample correlation. Does that make sense? Okay. And of course, just to give you the idea of the relationship, the idea of close, between -1 and 1, close to -1, how you can interpret all of that. Okay, do you know that the other time, right, we actually find the value of regression, right? Like we get a slope, and after getting a slope, we test how significant is the value, right? We can also do the same thing under correlation. If I compute correlation, if I have a correlation value, how significant it is. Why do we need to answer a question of how significant it is, because the value that we have, we want to prove to the world it is not just occur by chance. Okay? It does not just occur due to what I'm actually going to call accidental discharge of nature. And that was why we're actually also going to conduct a test on correlation after finding a correlation value. Just like the same way we conducted hypothesis testing on slope, we can also conduct hypothesis testing on correlation. But let me tell you this, for simple linear regression, when you are conducting hypothesis testing on slope, or you are conducting hypothesis testing on correlation, you are doing the same thing. You understand what I mean now? You are doing the same thing, but you're actually using a different procedure. Under the null hypothesis and the alternative, you're going to have rho equal to 0. You know the meaning? Rho equal to 0 means no correlation between x and y. It means no significant linear relationship. It's the same thing. Does that make sense now? Now, the test statistic here is going to be t equal to r minus rho. R is the value of the correlation. Some of you may be wondering, where will I get my correlation from? Oh, go back here. Come back to the regression output that we got. Where is the correlation value? You're going to go to the, do you see multiple r square, right? You take the square root. When you take, the multiple r square is 0.942, right? When you take the square root of r squared, that become a correlation. Does that make sense? Now, when you take the square root of that, you now want to test how significant it is. That exactly what you're trying to do here. So that is what you're trying to do here. R, the value that you got, minus the rho. What is rho? Rho is 0. Under the hypothesis, 1 minus r squared, of course, you know your n. By the time you plug all that in, okay, I told you, the multiple r squared, you've taken the square root of that. That gives you that, right? Okay, that is, which is the correlation. Now, by the time you now start plugging in, oh my God, take a look at something now. For simple linear regression, another thing you need to take note. For simple linear regression, the t-test for slope, the t-test value for slope is going to be the same t-test that gives you that, right? Okay, that is, which is the correlation. Now, by the time you now start plugging in, oh my God, take a look at something now. For simple linear regression, another thing you need to take note. For simple linear regression, the t-test for slope, the t-test value for slope is going to be the same t-test value for correlation. Let's take a look at this. What do you see here? 9.0099, right? That was the t-test value that we got. Let's go to the slope. We're going to go back to the slope. We're going to go back to the slope. What was it? What is the t-value here for the slope? 9.010. Do you see that? The t-value for the slope is going to be the same t-value for correlation. Does that make sense? Because whether slope or correlation, we're talking about relationship. So do you see 9.010, right, to 3 decimal is exactly what I have here. When you conduct the t, when you get a test statistic for the correlation. Do you see that? To 3 decimal, that would be 9.010. Okay? Now, how do I do this now if I want to focus on correlation test? This is it. Okay? Co.test. Do you see that? COR.test. Okay? Between square feet and sales method passing. In the end, this is the result. Do you see the result, the output? Do you see the t value? You see the p value? Oh my God. The t value here and the p value here will be the same as that, the one for the slope. What would be your decision? Compare the p value with the level of significance, you're actually going to reject the null hypothesis. What is the takeaway? When you are testing for significance of slope in a simple linear regression, it is the same as testing for the significance of the correlation. Does that make sense now? That is the takeaway. Any question? That is going to be the end of my lecture today. And we're done. We are entirely done with simple linear regression. The midterm one, we focus entirely on the simple linear regression, or what we did up to today. What we are starting tomorrow is a multiple linear regression will not feature in midterm one. Does that make sense to everyone? Okay, to have a recap on what I've done today. Of course, I walk you through inference. Okay, walk you through the inference. That we normally make on regression coefficients. And the only way to conduct an inference is to construct a confidence interval or to test hypothesis, which is what we have done. Why are we doing this? We're doing this because we basically want to know, even though the graphical means by residual plot that's already indicated that there is this a linear relationship, and we need to actually confirm further how significant is this linear relationship. And that is the reason why we needed today's topic that we called conducting inference on regression coefficient. And of course, you see that we constructed confidence interval, and we also test hypothesis. And of course, are also able to show that with simple linear regression, when you are conducting significant tests on slope, it is the same as conducting a correlation test. And that was why they give us the same value for p-value. And of course, the test statistic value was the same. And another takeaway from today's lecture for simple linear regression, relationship exists between a t-test and the f-test. When you square the values of the t, you're going to have the f value, okay? But they're basically going to have the same p-value, which means the same p-value means they're going to take the same decision. This is where I'm going to stop today. Any question before I go away? Any question? Somebody said, where can we find the midterm practice question listed on Canvas? The midterm practice question will be uploaded today. Okay. And of course, the TA will walk you through that on Friday. Like I said, your exam is going to be open. You're going to have access to exam on Friday by 6 p.m. And the exam will be left open for more than 24 hours. Even though you're only going to spend 90 minutes, you can start at any time. Okay, which means going to be open 6 p.m. on Friday up to 11:59 p.m. on Saturday. Look at that. That's a whole lot of time for you. You can decide to start at any time if you wish. You don't have to be flexible because I know you have a lot of activity going on in the summer. Okay, make sure you stay safe and have a lovely day. Bye for now, everyone.
Thank you. Have a good day.
You're welcome and have a good day too. Yeah.